Today we have got related rates. Related rates are equations that have a couple of quantities in them. You could even have as many as three, I guess. It's got two quantities, maybe three. We use the chain rule to differentiate both sides of the relationship between these two quantities. But what's different about related rates is we're taking the derivative with respect to time. So if we have the variable x, we're going to find the derivative of x with respect to time. If we have the variable y, we're going to find the derivative of y with respect to time. And so there will always be one of these dx dt's, dy dt's, d whatever variable we're using, dt. Let's just take a look at a quick example and jump right in with both feet here. Volume of a balloon is increasing 40 cubic centimeters every second. At what rate is the radius increasing when the radius gets to 20 centimeters? All right. Now, the method, or the acronym we use for this, kind of like we used DOFT for implicit differentiation. With related rates, we're using dead M&M. We are going to make a drawing. We're going to have an equation. Once we have that equation, that's when we're going to find the derivative. Remember, with respect to time. And then and only then do we start putting some numbers into this equation, into this derivative. And that is known as this magic moment. At that moment that we're talking about, in this case, this example up here, magic moment is when the radius reaches 20 centimeters. So let's make a drawing. We've got a balloon, and we'll assume that this is a spherical balloon. And the thing that varies in this thing is the radius. So we've got a radius here, radius of the sphere. And let's see, after drawing, we need an equation. So let's see. We're given some information about the rate at which the volume is changing. So I think volume is the quantity that's going to be pretty crucial here. The volume of a sphere is 4/3 pi r cubed. So we've got the drawing. We've got the equation. Now we're going to find the derivative. But we're going to take the derivative with respect to time. The two quantities that we're talking about in this problem are volume and how it relates to radius. So if I take the derivative of volume, that would be dv dt, the rate at which the volume is changing with respect to time. Now 4/3 and pi, those are coefficients on the r cubed, so they come along for the ride. And the derivative of r cubed, well, that would be 3r squared times the derivative of what's inside. And what is the derivative of r? So all quantities, just take the derivative the normal way. The derivative of v is 1. But I got to multiply by the derivative of what's inside. And the derivative of what's inside is going to be dv dt. All right, so now it's the magic moment. Now it's time to put some numbers into this thing. Well, let's see. The volume of the balloon is increasing, and if it's increasing, this is a positive 40. If we're decreasing, then it would be negative. So that is dv dt. Now this 3 and this 3 would cancel out, and we would be left with 4 times pi times the radius. Now this is the magic moment. And at the magic moment, the radius is 20 times dr dt. All right. I'm pressing pause. I'm grabbing my calculator. You do the same and we'll compare answers. All right. Well, I noticed one mistake that I had made. I forgot to square my 20. Now, if I square my 20, I think what I'm getting at the magic moment is that dr dt, the one unknown, is left 0.0079577, and it keeps going, going, going. Remember, we've got to be correct at 3 decimal places. If we were to truncate this at 0.007 or call it 0.008, either way, that's fine. And the units of radius are centimeters, and the units of time are seconds. So since we need dr dt, the radius is changing this many centimeters per second. All right. Now we got the ladder problem. Bottom of a 13-foot ladder is sliding away from a wall. That's not good. Hopefully nobody's on it. We've got a wall. Well, let's say that's a vertical wall. Not really well drawn. There's a floor. There's a ladder. So we're going to again assume that this is a nice perpendicular situation here where we've got a 13-foot ladder. Now, at what rate does the bottom of the ladder slide down the wall? At what rate does the top of the ladder slide down the wall when the bottom is 5 feet from the wall? Well, this isn't a 5 down here. This varies. This is a variable. We can call this x. This height varies as the ladder slides down, so that's a variable. That's good. Call it y. 13 does not vary. Ladder's always 13. So if something varies in the problem, you have to give it a variable. This is a magic moment number, not a constant. All right. So what's the relationship between these things in this drawing? It's a geometric figure. They usually are geometric figures. And so in this case, I think I would say x squared plus y squared equals 13 squared, which is 169. So I've got my drawing. I've got my equation. I now need to take the derivative of that equation. And the derivative of x squared is 2x. But I got to remember to take the derivative with respect to time. And the derivative of y squared is 2y. But I got to take the derivative with respect to time. And the derivative of 169, just like any other constant, it is the magic moment. And at this magic moment, we know the bottom of the ladder is 5 feet from the wall. Well, I could use this equation right here. If I know x and I know 13, can I figure out y? Or maybe I recognize a Pythagorean triple, where that's 5, this has got to be 12, if the hypotenuse is 13. So I'm going to take 2 times 5 times dx dt. The bottom of the ladder slides away from the wall at 1 foot per second. So this is a 1. It's sliding this way. Now, is that a positive 1 or a negative 1? I'm going to say it's a positive 1. It's a positive 1 because x is getting larger. When things get larger, the derivative is positive. So we now take 2 times y, and y is 12. But I don't know what dy dt is. But I do know that the result has got to be 0. Calculator time. Let's figure it out. Now I'm thinking I get dy dt equaling 0.416 repeating, or 0.417. And let's see, y was measured in feet, time was measured in seconds. And I do believe it came out to be negative. And it came out to be negative because is y getting bigger or smaller? As this thing slides down the wall, pretty easy to see that's getting smaller, we should expect a derivative that would be negative. Okay, water tank in the shape of a cone. Now, when it comes to cones, I think they're going to give you any volume equation that you might need. And cones are big when it comes to the AP test and questions that James has. So we've got this conical tank, 6 meters high, radius is 2, water pumped in 3 cubic meters per minute. So that's a volume. It's the rate at which the volume is changing. So I'm thinking volume is going to be important here. At what rate is the water level rising? When it gets to 3 meters. Well, let's draw this thing. We got this tank. And it is, now this is constant. This height here is 6. This radius here is constant. It is 2. But what's not constant is the water level. That's where this radius right here and this height right here, those things vary. But the height of the cone and the radius of the cone up at the top do not. Now we're talking about what's going on down in the blue down here. And so if I'm interested in the volume of any cone, it is 1/3 pi r squared times h, and that would be something you'd have to be given. Now when it comes to cones, looking at the cone overall is pretty important, because I've got 1, 2, 3 variables, and I want to whittle it down to as few variables as I can. Do you notice any relationship between radius and height? See, I think the height is the more important of these 2 variables, because at what rate is the water level rising? At what rate is the height changing when the height is at 3 meters? So I think what I'd like to do is I'd like to get rid of that radius and retain h's if I can. And I think I see that radius is always 1/3 of the height. The radius is 1/3 of the height. Since this is a nice symmetric cone, that relationship is always going to hold. So my volume equation actually is going to be written like this. 1/3 pi. Instead of an r, I'm going to say 1/3 h squared times h, which is 1/27 pi h cubed That's what volume is equal to. So I've got my drawing, I've got my equation. It's now time to take the derivative, and the derivative of volume is going to be dv dt. 1/27 pi. You're a coefficient, come along for the ride. Derivative of h cubed. And I got to remember to take that derivative with respect to time. And now, the magic moment. And in this magic moment, water's being pumped in. The volume is getting bigger at a rate of 3. We got a 1/27th. We got a pi. We got a 3. The height is 3, which needs to be squared. Not going to forget that this time. Times the one thing that we don't know, but our calculator is going to help us find. Well, I'm thinking that it turns out dh dt around 0.955, corrected 3 decimal places. And height is measured in meters. And time measured in seconds. All right, so let's take a look at one more example. Car travels west. Car's traveling west towards an intersection. "45 miles per hour. And actually, instead of saying a car, it should say car A. Car B travels north towards the same intersection. So I guess there's that intersection. So this is the A. This is car B. At what rate is the distance between the cars changing? So now I got 3 sides that vary, and I don't think I'm getting rid of any of these variables. So that's my drawing, my equation that relates these things, this geometric figure that I've drawn. A squared plus b squared is equal to d squared. So drawing equation, now derivative with respect to time. 2a times the rate at which a is changing with respect to time, plus 2b times the rate at which b is changing with respect to time, equals 2d times the rate at which d is changing with respect to time. And unlike the last problem, we're not getting rid of any of these. So it's magic moment time. We're going to take 2 times a. Now what does it say? At what rate is the distance between the cars changing when car A is 0.6? So A is 0.6. And A is traveling 45. Now, is that positive 45 or is that negative? Is A getting bigger or smaller? Well, I think you can see side A is getting smaller. That's a negative. Plus 2 times B. Well, B at the magic moment is 0.8 miles. And it is traveling at 55 miles an hour. And B also is getting smaller, so we have to consider that one to be negative. 2D. Well, if this is 0.6 and this is 0.8, You can use your Pythagorean theorem, or you can recognize this as a 6/8. Well, in this case, D is going to come out to be 1. If you don't believe that, plug them in, figure out D. Times what we're looking for, dt dt. So let's pause and figure that one out. Well, if your results are the same as mine, I think it comes out pretty nice. I think that dt dt is going to be negative 71. This distance right here is getting smaller. So that makes sense, should be negative. And distance is measured in miles, and time is measured in hours. So hopefully those examples give you a pretty good feel for how to attack related rate problems as you head into your homework for this evening.